Okay, I will start with the session for today. My iPad is so slow, sorry. Let me let it upload. Just dismiss for right now. Can you just show? Okay. While we're waiting for this to upload, how is everyone doing this morning? Kay, I just got your email, so we can talk about that later on. How is everyone doing this morning? I'm trying to get used to this new schedule. It's kind of just new because, yeah, I'm meeting a lot earlier than I did last semester. So, come on. Okay, hold on. Let me go out of here, try again. Ah, looks much better. There. Okay, so throughout the lesson, feel free to chime in if you have anything to say, or you can go ahead and use the message box to make comments, okay? If you have any questions, do the same, please. So hopefully you can see my screen. I am recording. I have to make sure I'm recording so that y'all can see this later on. So you can see my screen and I am recording, right? And you can hear my audio. So everything should be good. Well, this is the first day of class. We'll start with chapter E. And so unless anybody has any questions, I'm going to go ahead and start with chapter E. Now, at some point we should be seeing closed captioning, but I don't know. The feature sometimes works, sometimes it doesn't, so I don't know where it is. Anyways, I'll jump right into it. So we'll start with chapter E, which talks about the fundamentals, the things that you have to know before you study chemistry. In this chapter, we start with measurements. So the idea is in the lab, you will be doing a lot of different measurements. And as far as chemistry is concerned, these are the 7 base measurements we will ever do. Now, in general chemistry, when we do a lot of measurements, we don't get to do all of these measurements. At some point, we may measure length. Now, the length, depending on the object and the size you're measuring, it may be a large object or a small object. But for the most part, length is measured in centimeters or inches. And then in calculations, it's converted to meters. So you want to make sure that you know the 7 base units. So these are essentially 7 base units. And then you want to know the normal measurements, okay? The SI measurements. So for length, it'll be meters, mass, kilograms. Now, in the lab, you may actually measure it in grams, but to perform calculations, they will have to be converted to kilograms. Times will be measured in seconds. Temperature, once again, you may actually measure it in Celsius, but convert it to Kelvin for calculations. We never measure moles in the lab. We may measure mass, and then from mass, convert it to moles. But if we need to convert it to moles, we will use Avogadro's number, which may be in atoms or molecules, to convert to the amount of substance. Okay? Oh, I'm trying to figure out what happened here. My computer is slowly waking up. Okay, there. And then at this level, general chemistry 1, we don't deal with electrical current, but general chemistry 2, we do. And when we do deal with current, we'll deal with current in terms of amperes. And then we don't really deal with luminous intensity, but we study it. So these are the 7 base units. From the 7 base units, you can measure other measurements in the lab, such as volume or density. As you can see here in the measurements, volume and density is not a base unit. So these two are categorized under derived units. Why are they called derived? You use the base units, combinations of the base units to get the derived units. For example, to get volume, you essentially take length, multiply it by width and height. So volume is actually length cubed. Okay, so different combinations of the base units give you the derived units. density. To get density, you take mass divided by volume. Okay, so you have to solve for a volume first, and then from volume you get density. So essentially these are the basic units we'll see in the lab and the derived units. The different kinds of derived units. I've just chosen two. You of course also have area. You have many other measurements, right? And area will be length times maybe height. Okay, any questions about this? Once again, if you don't want to talk and you want to chat, just go ahead and type your message in the chat box. Okay, so they give you once again derived units here. And remember, with derived units you have different combinations of length, mass, and time. So we have examples here: density, volume, area, velocity. We will not be dealing with velocity a lot. We're not in a physics class, but you want to be aware that that does exist. Okay, so I'm going to move on to the metric prefix. Now, the metric prefix, you probably have seen this metric prefix. These prefixes, and they have new ones. I was actually listening to a program on the radio where they were introducing new ones, very, very large numbers and very, very small numbers. And I was like, oh my goodness. So the book we have has not been updated yet. Thank God for that. But we are learning about base units. Okay, so they will update it at some point, a newer edition, and then we'll get to learn all the new base unit prefixes. Okay, so with the metric prefixes or metric system, you do have prefixes that are multipliers. And these prefixes have a purpose. When I was learning this in school, I was like, why are we learning this? This is like, okay, whatever. But it does help scientists communicate numbers. And if you've had to write a lot of numbers over and over again and transcribe numbers, it's very easy to make a mistake, especially if the number is very large or very small. So the example we have right here is this very small number, or this very small number here. Or if you have a very large number, when you have to write it over and over again, the chances of making errors is very high. So to minimize errors, scientists came up with metric prefixes, okay? Or mathematicians, whoever, metric prefixes. So we use that to help us communicate very large or very small numbers. They're more useful there. So in the place of the very large or very small number, you use the prefix, and the prefix has both a name and a symbol that represents the amount of the number. Okay, so you're aware of mega, you're aware of giga, even though I don't have it right here in this table. This table is very limited, but you're aware of gigabytes for for memory storage in computers, megabytes, kilobytes. You're aware of all of that as far as computers are concerned. Now in chemistry, at some point we may use megahertz, describing frequency unit. We will use kilo. Sometimes we might use deci, centi, milli. When it starts to get small, milli, micro, nano, pico, we have femto. We have other smaller units. Depending on the object and the size of the object, you may be using any one of these metric prefixes. So if you're dealing with the mega and the kilo, it's understood whatever object you're looking at is large, right? Because mega stands for 1,000, 1 million, kilo stands for 1,000, right? So you get to convert the number to a more manageable number. So the original number provided to you, you get to convert it to a more manageable number using the metric prefix. So here we're being told N, which is nano, stands for this number right here. So 1 nano stands for 1 times 10 power negative 9 units of whatever it is you're dealing with or you're measuring. Okay? So to illustrate that in an example, if you have 641 nanometers, that means that length is very, very, very tiny. This is the same as 0.000000641 meters, very small. We tend to use nano measurements to describe the length of a wave. A wave is very tiny, and we sometimes don't want to use very small numbers to illustrate its length. So we use larger numbers that are more manageable, but in its place, to not compromise the value of the length of the wave, we use the metric prefix that fits. Okay? And then over here, if you want to describe or you want to talk about 1,000 kilograms, once again, you're dealing with 1,000 kilograms here, or kilo stands for 1,000. If you're dealing with kilo stands for 1,000. So in this case here, if you have 0.11 kilograms, the K here stands for 1,000. It's the same thing as 110 grams. Okay? So you want to be aware of metric prefixes. Now, at some point, I will talk about the different conversions. You have to know that from a base unit to a conversion that has a metric prefix, and then one where you have a prefix to a prefix. So it gets very complex at some point. But for right now, we're going over just the overview, okay? You want to be aware of the 3 temperature scales we talk about in chemistry. We have the Fahrenheit scale, the Celsius scale, the Kelvin scale. In the lab, we normally use Celsius and Kelvin. We rarely ever use Fahrenheit. Now, on campus, we do one experiment where we actually measure both Fahrenheit and Celsius to relate the two, okay? To see how Fahrenheit and Celsius relate to each other. We don't really actually have a Kelvin scale in our lab. So what we do is, if we want to get Kelvin measurements, we convert from Celsius to Kelvin, okay? I'm going to give you guys a table that shows you how to convert, but if you want to get Kelvin, just take the degrees Celsius you measured plus 273, to be specific, 0.15, and that will give you the same value in the Kelvin unit. Okay? So that's how you can go back and forth. And I'll give you guys a conversion sheet that allows you to go from Celsius to Fahrenheit. Now, we don't normally have a formula that goes directly from Kelvin to Fahrenheit. So if for whatever reason you have to go from Kelvin to Fahrenheit and vice versa, you want to go from Kelvin to Celsius, from Celsius to Fahrenheit. Okay? Does anybody have a question about that? If you're comparing the scales, please notice the numerical value of Celsius tends to be the smallest, and then Fahrenheit is a lot larger. So in your calculation, in your formula, you want to make sure you use the right formula to go back and forth, okay? So at some point, I will show you the table that has all these formulas to go from Celsius to Fahrenheit and vice versa. We do have this right here. In your slide, you see a formula, right, that shows you how to go from Kelvin to Celsius. And I gave this to you and vice versa. You can use that. So you want to make sure you write this down. And I'll tell you at some point what you need to write down, so make sure you're writing it down. If I'm writing it down, you want to make sure you're writing it down, okay? It makes it easier for you to be engaged in the process. Okay, so we use this formula right here to go from Celsius to Kelvin and vice versa, okay? So you're told here to determine the body's temperature in Kelvin. Once again, you will rarely, if you plan to be a healthcare provider, you will rarely ever figure out the temperature in Kelvin. You usually figure it out in Fahrenheit, but we're learning how to use the formula, so we have this example. The body temperature is 37 degrees Celsius, and we're being asked to convert it to Kelvin. So it shows right here. Take the value you're given, add 273, and I do have my calculator here. Even though the calculations are done, I think it's helpful for you to actually work it out yourself, because the goal is for you to know how to use your own calculator and get the hang of using it. So when I work it out, I get the answer. They get 310.15 Kelvin. We haven't worked on significant figures yet, so I won't talk about rounding up or down just yet. Okay? We'll talk about it when we get to it. Okay, here we're told liquid nitrogen boils at 77 Kelvin. What is its temperature in Celsius? So we're going from Kelvin to Celsius, right? So we know our normal formula is to get to Kelvin, take degrees Celsius at 273.15. So we're trying to get to Celsius, do the opposite, right? So take Kelvin, subtract 2 73.15. So we have what? 77 Kelvin minus 273.15. What do we get? So I'm plugging this in my calculator. 77 minus 273.15, and I end up with exactly what they have. Well, not exactly. Negative 196.15 degrees Celsius right there. Okay. Now they rounded up, but we're still learning this process, so I don't want to talk about rounding up or down just yet until we learn the significant figure rules. Okay. So I want to apply that in context. We'll talk about that down the road. Any questions about what we've covered so far? Okay. So we finally see the relationship between Fahrenheit and Celsius, like I told you guys. You probably have seen this before. To go from Fahrenheit to Celsius, degrees Fahrenheit is equal to, now they have this as 1.8. There are other formulas that have it as 9 over 5 times degrees Celsius plus 32. Okay, so the benefit you guys have is you have your notes, right? When you're doing your homework, you have your notes, you have everything else. You have PowerPoint slides to refer to. So back in my days, I say back in my days, it really was back in my days, we didn't have PowerPoint slides. The teacher had a board and a chalk in their hand, and then they wrote. So you had to keep up with notes. You had to, do a lot to get information, right? Many years ago. Anyways, so I had to memorize this quick because I'm like, I won't always have I won't always have a book to reference to find the formula. So it took me a while to get the logic that the Fahrenheit temperatures tend to have a higher value than Celsius. So when you're trying to go back and forth, remember to get the Fahrenheit, the number has to be larger. If you're going from Celsius to Fahrenheit and the Fahrenheit value is smaller, you flip the numbers or the positions of the Fahrenheit and Celsius. So make sure it's 9 over 5 times Celsius plus 32. And I'm saying this mostly for those of you who are going to take MCAT, PCAT, one of those CATs, or DAT exam, dental school admission test, medical school, or pharmacy school. You want to make sure you have this down. Okay? It's very helpful. Okay. So ultimately, if you take 9 over 5 multiplied by Celsius and then you add 32, the final number will definitely be larger, okay? After knowing this formula, the question is, your younger brother has a temperature of 40 degrees Celsius, probably has a fever, yep, has a fever. What is the temperature in Fahrenheit? So in Fahrenheit, you want to make sure you take you're trying to figure out Fahrenheit, right? Degrees Fahrenheit. 9 over 5. I use the 9 over 5 more than the 1.8 because for some reason that's how I learned it. So I remember that better than the 1.8. I mean, I see the 1.8. I prefer the 9 over 5. So the degrees Celsius we have here, 40.0 degrees Celsius, right? So right there, plus 32. So I take 9 divided by 5 and then times 40 degrees. It's a much larger number than the original number. That tells me I'm in the right path, plus 32. Okay, so I end up with 104.0 degrees Fahrenheit, like they have. Okay, I like the 9 over 5 once again because the larger number over the smaller number tells me my ultimate answer will be a larger number. So because of that security, I like to use the fraction. You can still use 1.8 because 1.8 is larger than 1. So whatever you multiply, when you take 1.8 times the number you have in degrees Celsius, it will also end up as a larger number. Okay. So use whatever works for you as long as it helps you get the right answer. Any questions about that? Okay. If y'all don't have questions, y'all are very quiet this morning. I hope you are awake. I feel like I'm getting more and more awake. I started off a little bit, yeah. It just takes getting used to the schedule. But yeah. So we haven't done the conversions yet. We're still trying to go through the definitions. Now we're talking about measurements and how reliable your measurements are, right? In the time of Corona, I know that was 2020. In this time, in the year 2021, right, where we're dealing with scientific work being published and everybody looking at science and the vaccines and all this stuff, all of a sudden, measurements and precision is a very big thing. You want to make sure that the work you put out there can be trusted, right? People are asking, can we trust the vaccine? Was the work done too quickly? Is there possible error in the work because it was done too quickly? So we have a lot of, possible human error. Well, they have done tests and they have published data. But the point that we're discussing right now is how can we trust the data that's produced in the lab? So we look at two concepts: precision and accuracy, and uncertainty. Uncertainty has to do with, trust, right? Can we trust something? Are we certain? Are we not certain? Precision has to do with measurements, right? Oh, yeah. And before I continue, does anybody know what precision is before you read this statement right here? Because we do have statements right here from the author, but I want to know if you guys had experience with learning about precision or accuracy in your previous chemistry classes. Has anybody learned about precision before? And if you have, good. What do you know precision to be versus accuracy? Because I've heard people use precision and accuracy incorrectly, and they use it very confidently too. They say precise when they mean accurate, or vice versa. They say accurate when they mean precise. So has anybody heard of precision and accuracy? I'm assuming yes, because I hear it a lot in the news. But when you learn about precision and accuracy, what did you understand from that before I get into my whole spiel? If you would like to share, it would be nice if you guys shared. Precision, anyone, or accuracy? The more common answer I usually get has to do with the target. So if you want to use the target to explain it, that works too. Whatever you understand, and then we'll take what you understand and build from there. Anybody? I guess I'll continue. Precision essentially is talking about, it says right here, agreement or closeness of a series of measured values. So when you're talking about precision, you're talking about consistency, okay? When somebody is consistent, you're saying they're predictable. You know exactly how they're going to act in a certain situation, right? You're like, oh, that person is predictable. They're consistent. They're who they are, right? What you're trying to say in that statement is you can trust them to behave a very particular way in an instant. You're not judging whether they're right or wrong. You're not saying, well, they're wrong for behaving this way or behaving that way. You're just saying they're predictable. Precision has to do with predictability. Oh my goodness, my spelling. I got distracted by the email. Okay, hold on. Ability. There, I think I got that right, right? So you take a measurement and you get 10.1 grams. So a mass, 10.1 grams. 2 seconds later, take another measurement. You get 10.1. Another measurement, 10.2. Another one, 10.0. And another one, 10.1. And then you conclude, oh, this experiment, these measurements are very precise. Why? I am able to get very close to the same results over and over again. Not usually in the lab. I don't know about you guys in the lab, but when I was in the lab with other people, I'm very competitive. When we were able to do something over and over and over again, we're like, yeah, that's how it's done. We're bragging. We didn't really like just diss other people, but we're like, yeah, that's how it's done. That's pretty much precision, predictability. We can do it over and over again. If you're talking about the basketball and hoop analogy, if you can throw the basketball in the hoop over and over and over again without missing, that is considered predictable or precise. Doing the same thing over and over and over again. Okay? Now, you can be missing over and over and over again, and you're precisely missing it, right? Now, in this case here, we're not judging whether it's correct or not. We're judging if you can do it over again. Okay. In accuracy, we're judging whether you're correct or not. So we don't really care if you can do it over and over again. Are you correct in what you're trying to do? So how can we tell if what you're doing is correct, right? So I've been trying to stay current, with the times and everything, and I keep hearing about truth and my truth and this, and I'm like, wow, this is very interesting. So when it comes to accuracy, there is a true value, right? So the true value is the value that scientists have gone to the lab, worked on, and said, this is the true value. And so when you are in the lab and you are trying to do your experiment, you are trying to match your data, your results with the true value versus saying, well, because this is what I got, this must be the true value. No, you're trying to judge your value with somebody else's value where everybody agrees that other value is the true value. Okay. So with each measurement you take with accuracy, you're judging it against an outside measurement. So if I take 10.0 grams, if I got that, we're judging it. What does the outside measurement say you should get? If the outside measurement says you should get 5.0, you're wrong, right? Because obviously your measurement doesn't match their measurement or the agreed upon measurement to be true or accurate. So it's about agreement or closeness. So this involves you and other people of an actual known value. So hopefully you walk away from here understanding this. So it is possible to be precise and completely wrong. And there are times when I'm like, okay, this is very precise, but it's precisely wrong. Nothing personal, but your equipment may be messed up, or there could be a lot of things wrong, right? Yeah. So hopefully you can see that. I don't have questions for you guys to participate. What I'm going to try to do is to try to bring in some stuff and collaborate for you guys to click on so that you can help me select the answers. Okay. But we want to be able to pick precise measurements from accurate measurements. So the difference here is with accurate, you need to have an agreed upon. So you need to have an additional measurement to judge your measurements against. Okay. So once you get the hang of this, then it's very easy for you to tell where the question is leading. So once I figured this out in school, I saw a question like this. I actually got excited because my question was, is this question about precision or about accuracy? So let's go ahead and move ahead. So when we look at precision and accuracy, the next thing we're going to be looking at is the term uncertainty. So what exactly is uncertainty? Uncertainty has to do with the level of trust. You're thinking, wow, this is science. We're not bringing our emotions. Yeah, we're bringing our emotions. Level of trust. When you're measuring equipment, can you trust your equipment? I can tell you something. I have this love-hate relationship with my scale. The scale that weighs me, it's mostly hate, a little bit of love, right? So I really feel there's a certain level of uncertainty in my scale. Recently, post Christmas and everything, Christmas, New Year, last year was the year of Corona. So we ate a little extra. We decorated a little extra. Everything we did was extra. So I stand on the scale. I'm like, let me see what the verdict is. I see the number and I'm like, that's a lie. That can't be true. This scale has a lot of uncertainty. This number is not true. I stood again on the scale. I got up and stood on the scale like 3 times, and the number would not change. I moved it to a different part of the ground. Y'all never do that because you're thinking it must be the ground. The ground is not stable, right? Because this number is too large. And I moved, and the number was still the same. So I moved to a third part of the ground, and I realized maybe it's not the ground. Maybe it's got to be the scale. It can't be me. Anyway, yeah. So uncertainty has to do with the instrument being used, like I told you. Okay. And I do try to dramatize this a little bit just to say that I want you guys to be able to look at things outside the classroom, right? Or the lab and see what we are learning. Like the scale. Can we really trust the scale? So we're being told here, when you buy instruments, even your scale that comes in with the kit, they do report the level of trust, the level of uncertainty, right, in the measurement. So if you have an instrument, for example, here we're being told that a device was used to measure the volume based on the unit, right, milliliters. And this volume is accurate to plus or minus 0.05 milliliters. So we have a number, and I'm going to write this out here, 23.45 plus or minus, that's how it should be written, 0.05 milliliters. That means this number you're looking at has some error in it. You may look at this number as the actual volume, but the actual volume, it says the true value lies between 23.40 to 23.50. Now, when it comes to my weight, you know what number I'm taking, right? The smaller one. I'm like, yeah, this is what my true weight is. And then I try to bring in that my scale, this is just me joking around with the scale, but I say my scale has a large margin of error, and then I take the smaller number, whatever makes me feel happy, I go with that and I move on. Okay. But yeah. So the true number lies somewhere between this and this. If you want to get a more accurate value or more true value of the in this case the volume, you want to buy a more expensive equipment, right? So you have the cheap equipment and then you have the really expensive equipment. In the lab, we have scales that cost $50 and some that cost $3,000, right? So obviously the one that costs $3,000 will give you a more accurate value. Okay, so you want to be aware of the level of trust as you're using the equipment. Usually it's called the uncertainty, right? So any questions? So when we're reading numbers, we're being told here, when you're reporting a measurement, the last digit is usually considered uncertain. So if we're looking at this, right, we read 23.45 plus or minus 0.05 milliliters. So when you round this up, or when you actually look at the value is between 23.40 and 23.50. So usually this would be reported like that. Oops, 23.4, 23.5, like that. And then this number here will be the uncertain number, the estimated number. So we will talk about measurements. And when we meet on Monday, I have some worksheets. I'll have some worksheets for you guys so we can work on how to read a graduated cylinder and figure out the value of the increments. Okay. So if your measurements has some numbers that are trusted and some numbers that are not trusted, how can we trust any measurement that anyone takes? Okay. And sometimes when we're measuring, and when we go over the graduated cylinder, you see how this plays out. Some people have to estimate the last digit, and so the last digit becomes the uncertain one. How do we deal with that? That's when the significant figure rules come in. So if you've ever had maybe high school chemistry or non-majors chemistry, you may have learned about significant figures, because I remember learning this somewhere in high school at some point, one of those, pre-college years. But I never really understood it in context. I just knew we learned about significant figure rules. We rounded up numbers. I just never knew why. It was a thing to do, right? You just did it. Why? Because if you don't, you get points off. But the context is we're trying to minimize error. so that if people are having to guess numbers, because somehow, you know, when you have the graduated cylinders, you have graduations or marks on the cylinder. If the measurement you're taking lands between the two graduations, you would have to guess what the value is. If you have to guess what the value is, and I guess differently from you, we end up with different numbers. But if we're doing the same experiment, the goal in chemistry when it comes to human beings doing stuff is for us to have a number that we can all agree with. So if I guess this value to be 24 and you guess it to be 23, they want to make sure we are at the same level. So when we start dealing with significant figures and how we round up, these rules here allow us both to round our numbers up or down so we end up on the same value. Okay? So our numbers are more consistent. And then when they're more consistent, they can be more trustworthy. Okay? So significant figures is to help us deal with this right here, helps us round off uncertain numbers. And these uncertain numbers are the numbers that you had to guess or estimate because they fell between two marked values on your instrument, right? My parents have the old school scale, you know, the one that has a little dial that goes back and forth, and I usually have to estimate my weight if it falls between the two things. I'm not measuring my weight a lot. I know I'm giving a lot of examples of weight. It's not like I'm walking around every day, you know, like 10 times trying to figure out what weight I have, right? No. But I'm just saying when I do go visit them, I try to figure out my weight and I'm like, I'm estimating on the low end. Right. When you have to estimate, guess what the value is because it doesn't land on a number, they want to make sure in the end they round off the number that you had to guess because guessing causes uncertainty. And when it does, we round it off using significant figures. Okay, we'll go ahead and move on. Before we talk about reporting significant figures, comparing measured values, exact values with guess values, we have to learn what exact values are. So you're given examples here. These are considered exact values because they don't change based on the situation. 1 inch is equal to 2.54 centimeters. This is an equality. An equality just means that you're measuring the same, in this context here, length, but you're reporting it in two different units. So if you measure 1 inch, the length of 1 inch, let's pretend this is 1 inch. If you measure it in inches, it will be 1 inch. If you measure it in centimeters, it will be 2.54 centimeters. Two different numbers just because you have different units. Okay, these values do not change ever because the relationship is fixed. So because they are fixed values, they're considered exact values. This is exact because it's fixed. So exact means fixed, doesn't change. This relationship here, regardless of the day of the year or the day or the time or whatever, 100 pennies will always make $1. So all of these are exact or fixed relationship. So because they're fixed and they never change, they're called exact values. But when you're in the lab and you're trying to measure something and the value falls between two marked points, that has to be estimated. Okay, and that makes a difference. So you just want to be aware of that. So we are segueing. Once again, next week I'll bring some examples for us to work on so it's more interactive versus just me doing all the talking. Okay, here, significant figure rules. So you probably have done this before. If you haven't, we're learning how to count significant figures because we do have one rule. And in chemistry, in this context here, one objective. Our objective is consensus. Be on the same page. The same page about the measurements that we are taking. So if I measure it, I get the same number. You measure it, you get the same number. Even if we have to estimate, we get the same number. So this is same number. Of course, after rounding. So sometimes in the lab when we're doing experiments, people in a group, one table will get like, 2.5, the other one will get 2.6, and then they're both asking me, well, are we right? Because our number doesn't match theirs and it's different. I'm like, yeah. Well, if you guys have similar values, yeah, you're both right. Why? Because in my head, I'm thinking the significant figure rules will reconcile your numbers. You will round up or round down. You take averages and stuff, and that will help you minimize the error and you all be on the same page. Okay. So, counting significant figures. Number one, now we're learning the rules, right? Number one, you want to look at numbers, and if you have non-zero numbers, all non-zero numbers count as significant. Now, significant does not mean important. I know in English, significant means important. In this context here, significant means what we are observing for the purpose of being on the same page. Okay? Years ago, I had this student in the class who got upset because he was angry at me. I'm like, I didn't write these rules, I'm just teaching it. And he was angry at me because I was calling certain numbers not important. And I was like, not for the purposes that we're trying to do, which is to be on the same page, right? This is the goal. For the same page, certain numbers will count as significant, certain numbers will not count as significant. So I just thought it was interesting. I have never forgotten him or what he told me. Anyway, number one, all non-zero numbers are significant. So in this number here, 536, 5 is significant, 3 is significant, so is 6 because none of them are zero. Okay, so this number here has 3 significant figures. Any questions about that? Okay, now the context is chemistry lab, right? Not money in the bank. Because all them zeros, if you have a bunch of zeros after a number, those zeros better be significant, right? So the context here, these rules only apply to lab measurements and chemistry and lab measurements, okay? Number two, zeros between non-zero digits or numbers are significant. So 6703 has 4 significant figures because, of course, the 6, the 7, and the 3 are significant. But the 0 is also significant because it's sandwiched between 2 non-zero numbers. Okay? Zeros between 2 non-zero numbers are significant. Okay, so hopefully you're writing this down. And then we're starting to deal with the zeros. So in this section here, in the rules, the zeros are the ones that get complex. Okay? Number 3, we're dealing with leading zeros. We're told leading zeros essentially are usually not significant. They're placeholder zeros to the left of the non-zero numbers, and for that reason, they're not significant. So what they're trying to say is when you have these zeros before a number, they're leading. You see them first before you see the non-zero number, so they're leading. At least that's how I interpret it, right? You see them first, then you see the non-zero number. So the 0.00, these are leading zeros. These 3 zeros here are here to communicate to you this number is small. How small is it? It's small. Oh, sorry, small. Right? It's small based on how many zeros you have before the number. If you have this number versus 0.000043, you know this number is much smaller because there's a lot more zeros before the actual non-zero number. So these zeros have a role, but the role has nothing to do with the consensus. But it has to do with communicating to you that the number is very small. For that reason, we don't count those zeros as significant. Does anybody have a question about this part? This part is where it starts to become murky, right? Zeros before a non-zero number is not significant. Okay. Once again, even if you have a question after I've passed the point, feel free to write it in the chat or the message box. I can go back and explain it, okay? I am here for you to help you guys out. Don't feel shy about writing stuff down. Okay, trailing zeros. This is the one where people go like, what? This is the one where the guy lost it. I was like, oh, I'm sorry about this. I'll call the author. He didn't make these rules up either. Anyway, where was I? Number four. Trailing zeros. Trailing zeros. These zeros, these are zeros to the right after a non-zero digit, and they're not significant. Okay. Now, context is chemistry. So if we write 1000, just like that, grams, these zeros here, for the purposes of making sure everybody gets the same numbers, numbers haven't been improperly estimated, that purpose, these zeros are not significant. But they are significant in communicating to the person making the measurement. This is a large mass, especially in chemistry lab. This is large. Okay, so the more zeros you have, the more you're communicating very large. But in the purpose, which was being on the same page, estimating correctly, having the same number after rounding, this is not important. It's not significant. Okay? So for that reason, we'll say this number here only has one significant figure. Oh, I forgot to say, this number here only has two significant figures. Only the non-zero numbers count. Okay? So for this last part here, let me get a little bit more involved and actually add a page. Oh, by the way, if you're wondering what app I'm using Notability app. If you came in earlier, you saw me actually trying to get this on Notability. So it's like Notability. Okay. And I'm using an Apple Pencil. Oh, disclaimer. Nobody's giving me any royalties. This is not a YouTube channel. No, the companies do not see Blackboard at all. So in no way am I getting royalties for this. Nobody's paying me for this, so sad. But yeah, and I'm using the Apple Pencil because when I started teaching these classes online and doing the live lectures in spring, one of my engineering students logged on to ask me about the lab. Now I'm watching his video. He's showing me his screen. He pulls out, I thought, I don't know, it was an iPad. He pulled it up. He had the lab on there and he's writing and he's asking me the chemistry question and I'm answering. But I'm like, and then I tell him, oh, that's wrong, right? That's wrong. And then he takes, it looked like a pencil to me or like a pen, and he just erases it like that. He does this. And I'm like, whoa, what are you using? He said it's an Apple Pencil. And what's that? An iPad? I told my husband, that's what I want. I know I'm a nerd like that. So then my husband got that for me for my birthday. I was like, thank you. So it helps me a lot to not have to print a lot of stuff. So just in case, you don't have to get that stuff. I'm just saying, just in case. If you have a stylus, the stylus works too. It's just I write a lot, so it's easier for me. Anyway, back to what I was doing. Yes, this has one significant figure. Then over here, I'm going to write this number down here, 32040. For this down here, let's see. This is significant. This is significant. I'm starting with the rules, right? These three numbers for sure are significant. This zero here, because it's sandwiched between two non-zero numbers, is significant. And then this last one, though, is a trailing zero. For that reason, this number doesn't count as significant, but you don't leave it out. You have to leave it there because it does have a purpose, right? It's communicating the magnitude of the number. So you will say this has 4 significant figures. You want to break it down and apply the rule one at a time. Okay? Any questions about that? So when are the zeros significant besides when it's sandwiched between two non-zero numbers? So I'm going to ask this question here. When are zeros significant? Number one, we saw when it's between two non-zero numbers. Between two non-zero numbers. That's number one. Okay? Like 101 is 3 significant figures. Number two, when you have a decimal. So I'll say when there is a non-zero number to the left and a decimal to the right. Okay? For example, if I say 60 dot, my teacher used to do this in college, and I'm like, what is that? Like, who did you mean to write more? No, these are two significant figures. Because she would write that, and I'm like, that's so old school. Then once I learned the rules, I was like, oh, now I see why she was writing that. And I'm like, okay. So 6.0 dot, okay, 6 is definitely significant based on the rules, right? The 0 right here is significant because it's sandwiched between a non-zero number on the left and a decimal on the right. So that makes this significant too. Any questions about that? So everything I'm saying is clear? No questions? Yeah? So as long as you have non-zero numbers, so I'm always doing a check, right? Once I figured out how to apply the rules, I became like I'm not the manager, whatever. I was always checking. Does it fulfill the criteria? Is there a non-zero number to the left? Is there a decimal to the right? Thank you, Victoria, finally making me feel like I'm not alone here. Okay, so let me add the third rule, and then I'll answer Victoria's question. So the third rule is when there is a non-zero number to the left and a decimal to the left. All of these are happening to the left, right? Okay, so here I'm not saying that the 0 has to be between the decimal and non-zero number, but I'm just saying somewhere to the left of the 0, there has to be a non-zero number and a decimal, okay? So to answer Victoria's question, I put 60.0 here. Okay, so based on the rules, 6 is significant. 0 is also significant based on this rule number 2 here, right? Because if you look at the 0, to the left there's a non-zero number, to the right there's a decimal, so this is significant. Now, based on rule number 3, the one I just said, there is a non-zero number to the left of my 0. Yeah, this one to this 0, right? This one here. And there is a decimal. Yep, this one here. So that makes this significant. Therefore, this has 3 significant figures. So I essentially applied the original rule number here, where all of them, yeah. I applied the original rule that said that if you have a 0 number, it's significant. And then for the zeros, I applied, what was it? The second rule and then the third rule. So if I say, let me give you guys a hypothetical question. If I say 1003 point, 0.00. How about that? I know, I just had to throw that in there. Okay, what do you guys think? How many significant figures do I have in this number I just made up? You want to judge each 0. Each 0 must be judged. Okay, hold on. Definitely these two are significant, right? Based on the other rule, these two are significant. Based on the rule we just learned, this is significant. This is, so let's see, 1, 2, 3, 4, 5, 6, 7. Yep, 7 significant figures. Very good. Yeah, take your time with these questions. Don't rush, right? Because it's you're applying the rule. When it comes to applying, you applying means judging. You're judging. Is this or is this not? Right. It takes a while, but once you figure it out, it's good, you know? Once you figure it out, it's good. Oh, so we have questions here, I guess. Okay. Now, here we're going to be judging because the answers are already there. We're judging to see if this is true, right? Based on the rules we had. They're saying these have 5 significant figures. Let's see. Okay, based on the rule that says all non-zero numbers are significant. So yeah, these are significant. These are sandwiched. So I'll call this a sandwich rule between 2 non-zero numbers. So yeah, they're significant. This is correct. What kind of zero are these 2 zeros here? The ones that come after a number, they're kind of like following the number versus before the number. When they're after the number, they're called trailing zeros, right? They're kind of trailing behind, kind of like lagging behind. So these numbers are not significant because their only role is to communicate how large this volume is. So only this number here is significant. Okay, so yeah, Monday I need to write a note to myself because when I get done, I relax and I'm like, oh, I'm done. So this is for Monday's lecture. I said I was gonna bring a volume measurement for us to do together, volume for grad cylinder, and then I'll bring some significant figure questions where the answer is not written, sig, fig, and we'll start from there. Okay, this one here, so yeah, this is one significant figure, that's true. This one here has 0.04450. This is leading zero, so it's not significant, not significant. Now, when we're saying not significant, we're not saying leave them out, right? Because some people leave the numbers out. You can't change the value of the number. You're just not counting it as significant. You want to leave it in your calculation, okay? So leave that out. I mean, sorry, you want to not count it in your calculation. Just leave it as is. So this is not significant, not significant, 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 significant. Look to the left of the zero. Do you see a non-zero number? Yeah, there's 3 of them. Do you see a decimal? Yep. So this is significant. So this would be 4. Okay. As I said, sadly, we don't have problems here, so we're just going to have to go with what we see right there. Then they're telling you with this one here, when you have an exact number, right? Remember the exact number, this will always be that number. 100 centimeters will always make 1 meter. This number is exact. Because it's exact, it has unlimited number of significant figures. We don't really have to round this up or down. Okay? So we're told they're always 100 centimeters in 1 meter, never 999. Never 99 centimeters in 1 meter. So 100 is treated as an exact number. We don't do significant figure rules on these exact numbers. So I would say once you start working on your homework, and I suggest you start working on those, just kind of try some around to see how you're doing. You would get what I'm saying. You don't do significant figure round ups or down on the conversion factors. When I was in school, they didn't tell me this, so I just did stuff. I did a lot of wrong things before I figured what was the right thing to do, right? I should have a TV show called What Not to Do in Chemistry. Nobody will watch it, though. Not for entertainment. Okay. When it comes to scientific notations, you want to know how to read significant figures. We only focus on the base number. The base number is this number right here. Oh, I remembered. As I'm doing stuff, I'm thinking about what to do on Monday. I remember they don't spend a lot of time in this book talking about scientific notation. So I'm going to make sure the stuff we do on Monday has scientific notation. They don't do a lot here. Okay, so once again, Monday we'll start with a quick review of what we've covered today so you can have a chance, because it's so important for us to know how to deal with these numbers so that when we're doing calculations later on, it's not a problem down the road. Okay, so in scientific notations, you tend to have 2 parts of the number. This part here is called the base number, the regular looking number, and then you have the exponent form. Okay, so the base number usually is somewhere between 1 and less than 10. So let's say the number, let's call it A, is between 1. It can be equal to 1 and then less than 10. Yeah, like that. And so with this number here, once you see the number, This part, the base part of the number, is the number that we are assigning significant figures to, not the times 10 and the power, just the base number. So according to that number, this will have 4 significant figures, because if you look at this number right here, these 3 zeros, right, have a non-zero number to the left and a decimal to the left. So it all boils down to what's happening to the left, right? So these 3 zeros are significant for that reason. This number has 4 significant figures. So hopefully you're writing these rules down, right? Paraphrase them in your notes. With the scientific notation, you're looking at the base number only. Same thing over here. Look only at this number. This number is significant. This number is significant. This number here is sandwiched between a decimal and a non-zero number. So it is significant. And then this last number here to its left, it has 2 non-zero numbers and a decimal, making it significant. Therefore, it has 4 significant figures. Okay, you're judging each number to make sure it's significant. Okay, so like I mentioned, right? I mentioned this, that we will be working on this to get more practice, because we only do one, but it's important to know how to read instruments in the lab. So we're going to be looking at precision of laboratory glassware. Can you trust the glassware? Are you using the correct glassware? And the last digit. Why are we focusing on the last digit? This is usually the one that you guess, the one that causes uncertainty. Uncertainty, right? Because when you're guessing, like, well, if you're guessing, you don't really know, right? We can't trust you in anything. So the one that you guess is the last digit. So we're told here, for instruments marked with a scale, you determine the last digit by estimating between the marks. It's that whole estimating, right? You're kind of looking, you're squinting, depending on your eye position, you can guess wrong. So for that reason, it tells you that the way you're going to read this is to say mentally divide, oops, wrong thing, mentally divide the gap between the marks into tens. Then estimate which tens the indicator mark would be pointed towards. When I do this, I don't do all that when I'm trying to measure my weight. I just look at the number, the value between the two. Let's see. It's a scale, right? So let me draw that differently. I'm not measuring my scale. I'm like, okay, you have these marks right here, and it's pointing right here. And I'm like, ooh. So even though I know it's kind of between these two, I read it like this. I told you, whatever makes me happy. I mean, who is there to judge my work? Who is there to judge the accuracy of my weight? Nobody. I have fun with it. Okay, I have fun with it. Okay, but since we're in the lab, you want to make sure you're being accurate as much as you can. So we're going to learn how to read this value here. You want to estimate the value first and make sure what each line stands for. So since we're measuring between these 2 points here, remember this is 4 and this is 5. And between 4 and 5, we have these graduations. So you want to count the spaces between the graduations, right? Not the actual marks. I used to count the marks, and that used to confuse me, because people say count the marks. It's really the spaces. So 4 and 5, right? Essentially between 4 and 5, I'm assuming this is milliliters. We have 5 minus 4 milliliters. So we essentially have 1 milliliter, right? The space between these 2 points right here. We're trying to figure out what the value of each of these spaces right here is. The space here, it's hard to show, but yeah, between the marks. We're trying to figure out what that space is. So let me count and see. I know I have 1 milliliter. It's divided into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I have 1 milliliter divided into 10 spaces. So I can say it's 1 milliliter divided by 10, which makes 4.1 milliliter. So each of these spaces is 0.1 milliliter. So halfway point between the 4 and the 5 is going to be 4.5 milliliter. That makes sense. Okay, so we're doing good, right? Now, when it comes to reading the actual value, you can see the meniscus. When you're reading, you want to make sure your eye level is right here. So you're looking at the bottom of the meniscus. Maybe my eye is a little high, but the bottom of the meniscus right there. Okay? The bottom of the curve. So you can see here that the bottom of the meniscus of the curve lies between 4.5 and 4.6. Those two marks. You start with the places that actually have marks. 4.5 and 4.6. We know this is 4.6 because I just added 0.1, right? So your true value is 4.5, and then you're going to add an extra value here. So the question here is to try to guess or estimate what you think this value is right here. Remember, you're counting from bottom up, right? What do you think this number should be? This number is a fraction of this space between here and here. So do you think it's like halfway through? Is it a little bit above half? Let me erase the mark so you guys can actually see the number well. I'm going to zoom it in. What do y'all think? What number should I place right here? Is it about halfway? Are we talking like 0.05? Like halfway, or is it like a 3/4, or what do y'all think? For this exercise to work, I need a bunch of people, like I need many people giving me answers so we can go ahead and judge. And so we can see how estimating plays out. So the goal is not for you to copy somebody else's number. Tell me what you see. Like if you were to report this, what would you report? So I'm trying to figure out what number I should, oops, wrong thing. I'm trying to figure out what number I should write here. What do y'all think? Because it's not at 4.6. We're not at 4.6. We haven't gotten there yet. We are between 4.5 and 4.6. But I'm trying to figure out what number goes there. Am I halfway through, like at a 0.05 level, or am I a little bit over that? Anybody? You can give me the number in whole numbers, like 1, 2, 3, 4, 5, 6, and then I can just put the number on there. Okay, thank you, Alifia. Is that how to pronounce your name, Alifia? Thank you. Okay, so 4.55. So she's thinking that it's halfway through. Okay, so I write 4.55. Anybody else? I say it's 4.57. Does it make me more right than her? No, that's just how I see it. Anybody else say a different number? Okay, I'll make up some other numbers. We have 4.56. We have another 4.55. And then we have all these numbers, right? So it's obvious that you can see the 4.5 actually marked in the graduations. All of us had to guess that last number. So the last number that we're guessing, this is the uncertain part. All the significant figure rules that we are learning later on, that we're going to be rounding numbers up and down, allow us then to round our numbers. So later on, we'll learn the rules of how to round the numbers, but I'm going to write them here. I'm out of space on the right. So we know how to run numbers from math, right? If you've at least had math, you know how to run numbers. So I'm going to write this here. 4.56, 4.55. Okay. So in rounding numbers, we are rounding off the estimated number, not the numbers that were certain. So please notice, right? Here we have two parts of the number. The certain part was the 4.5. We all agree on the 4.5. There's no question about it because we actually have a mark for it. The number that comes after that, this number here, that's the uncertain number because we had to guess. Uncertain, if I can spell. Oops, I pressed the arrow, right? The uncertain number. That's the one we had to guess. So we're trying to round this number off. based on the mathematical rules of rounding, since this number is 5 or above, you round up, right? So when we are approximating, this top number will be 4.6. Mine will be 4.6, 4.6, 4.6. And all of us are now at the same number, even though we all estimated our last number differently. Okay? So this is, at this point here, we have consensus. We all agree. Here, we didn't all agree. We all had our own opinions about the last uncertain digit. So you can see significant figure rules that helps us to round up or round down, helps us to get to the same page when it comes to measurements. Okay? And the idea here is to minimize error, of course. Scientists are trying to make sure that their answers are correct. So they're telling you here, yeah, in words, their meniscus lies between 4.5, 4.6. So versus having a question about, is my last uncertain number? Now, there is such a thing as a wrong uncertain number, right? If you said 4.51, will be like, really? Really? Where'd you get the 1 from? It looks like it's above. The mark is way above the half point, right? Or at least it's above the half point. So you can tell it's definitely not at 1 level. So this one here we'll think is a little suspect, right? So we're told the meniscus rests between 4.5, 4.6. So you want to see that the graduate center has markings every 0.1 milliliter. So they read their number as 4.56 milliliters. With the 4.5 being the certain number, we are certain, we are sure of this. And then the sixth part, the 0.06 being the uncertain number, because we had to guess it. Okay, we had to estimate it. Any questions about that? Okay, so, oh, they briefly talk about scientific notation. With scientific notation, I've seen this done very weirdly in other chemistry books. Weirdly enough, chemistry authors have different ways of getting to the same problem or same answer. So I read something somewhere recently and I was like, what is this? Scientific notation. So it's briefly, very briefly discussed here. Converting this number to scientific notation, remember, in scientific notation, you have a base number. So this is a base here. And then you have the 10 times 10 power. Then you have the exponent. So you have the standard number. You have times 10 and then the exponent. So the exponent you have here, it's according to where you place a decimal. So starting with this number here, I'll write this as 3010. This becomes 301 or 0.1 times 10 power 3. So how do we get the times 10 power 3? First of all, on this original number, you place a decimal all the way to the right. So you don't want to change the value of the number. So you place a decimal to the right of the number, because there isn't a decimal that came with the number originally. There isn't an original decimal. Place it to the right, and then move the decimal to the left so that you end up with one non-zero number on the left. So I have to move this decimal 3 spots. 1, 2, 3. Make sure you have one non-zero number to the left, because your base number that you have here can be 1, but it has to be between 1, this number here, and let's see, can be equal to 1 or greater than 1, and it has to be less than 10. This base number can never be equal to 10. I forget how they say it in math, so I'm just going to describe it. It cannot be equal to 10, but it can be very close to 10, but it can be equal to 1, so essentially between 1 and 10, but never equal to 10. Okay? So if I move my decimal 3 spots to the left, I end up with a number 3.01 that fulfills this criteria. It's above 1, but less than 10. And then since I moved my decimal 3 spots, I write 3 here. Now, I think what they were saying in their rules, which is kind of interesting, is your final number that you have, the base number, less than the original. If it is, you leave this as positive. If it's more than the original, change this to negative. I like to say when you move to the left, leave this as positive. If you're not sure, put this in your calculator and then press equal, and you get the original number. So if you're still uncomfortable with this and you're learning that, just plug in whatever you have in scientific form in your calculator, press equal, convert it to a regular number. It will show you the number, and that will give you a little bit more confidence about what you're doing. Okay. I know some of you have math anxiety and then chemistry anxiety, and then it all kind of compounds together, right? Yeah. So here, with this number here, we have an original decimal in the number. So in this case, we can't move it left to get our number to be between 1 and 10. We have to move it right. So I move it 2 spots. So when I move it 2 spots, I end up with a number 3.10. Please notice this time you want to leave out the leading zeros, because our goal is to end up with a base number that's between, I say between 1 and 10 because it's a lot easier to say. That's between 1 and 10. It can be equal to 1, but it cannot be equal to 10, right? So between 1 and 10. So this is the number I get left with when I move the decimal twice. Let's see. Twice, that means times 10 to the negative 2, because I moved 2 spots to the right. And this is my final answer. Once again, if you're not sure about this, plug this number in your calculator, press equal, and it will give you the original number to tell you that you wrote the sign up here correctly. Okay. So here we finally have some questions, some review questions. We're told here, how many significant figures are in each number? Okay. So what do y'all think for A? I'm just going to confirm the answer as yes or no as I take a break here. For the first one, what do you think? It's 554 kilometers. How many significant figures do I have for this number? Okay, very good. 3 significant figures. And then 7 pennies. Seven pennies. Any takers for that? I know if you're reading ahead, if you have the PowerPoint open and you're reading, okay, if you have the PowerPoint open and you're reading ahead, you see the answer they gave you, right? And they're saying this is an exact number. Now, this is where some books, not just books, but the authors disagree. Just so you know, even though the goal is for everybody to be on the same page, everybody is not on the same page, even when it comes to the rules, right? This author, Tro, he says this is an exact number because 7 pennies will always be 7 pennies. If you count 7 pennies and somebody else counts 7 pennies, they can't come there and be like, well, I think this is 6 when they have 7 pennies. Like, everybody will agree 7 pennies are 7 pennies. Versus when you're measuring a distance, depending on the device you're using, you can be a little bit off, right? So yeah, so they say this is an exact number and therefore unlimited. Now, if you're working out a problem on the exam, you will rarely have I will rarely assign you something ambiguous like this. But if you were working out on a problem in the exam, and instead of having the unit pennies here, if this said 7 meters or something like that, oops, sorry, then you will count this as one significant figure. Because pennies you're just counting. So when you're counting, you either have 7 pennies or you don't have 7 pennies. There's no estimating there. You get what I'm saying? But if you're measuring 7 meters, this will be one significant figure. So I get why they put that here, but it can be a little confusing. So for 7 pennies is unlimited significant figures. But if it was 7 meters, it would be one significant figure. Okay. So I'm trying to get you guys away from memorizing to understanding why the answer may seem off. Because I have people saying, well, why are they saying this? If you're counting objects, then everybody should arrive at the same number. There's no estimating. Okay. So hopefully what I'm saying makes sense. It's one significant figure if the unit was meters, that meant you were measuring. But if you're counting 7 pennies, then this would be an exact number because you're counting. And because it's an exact number, it will have unlimited significant figures. Okay. What about C? What do y'all think? C. C is a scientific notation. 3. We only look at this number here, not that, not that. 1, 2, 3. The 0 is sandwiched between, so we have 3 significant figures. Okay. And then time, we measure time. So what do you say about time? The time is okay, yeah, these are all leading zeros. This is telling you very, very little time. So this counts 2 significant figures, right? Let's see. E, 1.4500 kilometers. This is a measured value, right? It's a measured, it's not counted. They had to measure it. So what do we say about that? The rest of you don't, I mean, feel free to chime in. But yeah. What do y'all think? Victoria, you can't have 2 answers. Okay, 3 or 5. Okay, let's examine both. Okay. Let's see. Where was I? You make me laugh. Okay, so the 3 legitimately 1, 4, and 5 are definitely significant, right? Because they're non-zero numbers. Let's look at our zeros though. To the left of the 0, do we have a non-zero number? Check. First requirement, right? Do we have a decimal? Check. That's true for both zeros. So here's the thing. Thank you for doing that actually, Victoria, because when you're going over your PowerPoint, I had to learn this in chemistry and I was like, man, my brain is a lie. When you're looking over your PowerPoint and the answer is provided, I'm like, oh, I got this. I'm like, yeah, yeah, that's how you do it. Uh-huh. And then when I have to answer a question where the answer is not there, I'm like, oh, wait, what was the rule again? So that happens to me sometimes to where I am kind of second guessing myself, right? But yeah, the rule is look at your zeros. To the left of the zeros, do you have a non-zero number? Yeah, we actually have 3. Do you have a decimal? Yeah, we have decimals. So since both zeros have a non-zero number to their left and a decimal, they're both significant. So we have 5 significant figures. That's why you want to practice questions where you don't visually see the answer, so it can kind of help you resolve those questions you may have had but you didn't know you had. Okay, F. What can we say about F? We can have a whole discussion point about this F. What do y'all say? Okay, so if you were given a question like this and you say 2, I'll be like, yeah, sure, 2 works, right? 2 works, 2 significant figures. Now they go into the whole dialogue that, well, this is not clear. I'm like, it's pretty clear. It's 2, right? Because this is a comma, not a decimal. So they go into a whole dialogue of this is ambiguous, because if the person meant to say 2 significant figures, the best way to do that would be to write this in scientific notation as 2.1 times 10 power. Wait, there's no decimal here, right? So to be clear, I guess this is kind of unclear. If you ask me, it's pretty clear to me. Decimal here, move to the left. 1, 2, 3, 4. So they're saying the more clear way to communicate two significant figures is this way. I mean, I agree there's a more clear way, but I think this is pretty clear, you know? So I don't necessarily, oh, they don't have answers here? I thought they did have answers. Yeah, they tend to say this question here is a little ambiguous, but if you were working a problem out, see this as two significant figures, this and this. Remember, these are the same numbers, okay? So we're going to work out operations here, adding and subtracting significant figures. When I teach, it takes me back to my youth, the days when I was young and I was struggling with this stuff. The struggle was real. When you're dealing with adding and subtracting versus multiplying and dividing, so mathematical operations here, remember, adding and subtracting goes together, multiplying and dividing goes together, okay? So we're told mathematical operations dictate the reporting of significant figures in the answer. So in other words, the operation drives what you do and how you count the significant figures. So what I want to do here is I want to start with adding and subtracting, because somehow I feel like when I start with multiplying and dividing, then people kind of forget adding and subtracting. Okay, of the two, I would say this is a little bit harder. Okay, at least I teach from my experience, the experience I had, and my experience was most of the stuff was hard. Okay, so I would say of the two, this was a little harder for me to remember. So I'm going to start with that. I want this one to be in your brain and then to remember that. That way, this is a lot easier than multiplying and dividing. So for the harder one, what we're going to do here is, it says the value with the smallest decimal measurement determines the answer of the significant figure. Okay, this is so significant. What I'm trying to say here is when they say the smallest decimal measurement, that is what we're checking for. The rule is, they haven't said this, I'm paraphrasing, line up numbers. Ooh, if I can spell, numbers to get smallest decimal place. And then after you do that, then your answer should have the smallest decimal place you were able to figure out. So first of all, you line them up. Are we going to line up anything in multiplying and division? No, we won't line up. So here I say no line up. With adding and subtracting, we line up. Having taken a lot of chemistry, I learned a lot what not to do, because at first I was figuring it out myself, right? Because it wasn't being clearly communicated, and I wasn't very confident in what I was doing. So I read and I second guess myself a lot. Then later on, talking with people, studying with people, I started learning, oh, I can actually bring myself into this lesson, right? There are good ways of doing things and then there are bad ways. So once I learned the lineup method, I was like, I am going to be lining up from here on. So when you line up, it mentally tells your brain you're doing something different on purpose. So you line up your numbers, get the smallest decimal place, and then you use that to figure out your answer. So we'll go with that first, and then we'll come back with the multiply and divide. So let me see. I'll skip this page, come back to it, go to the line app. Okay, so here we are lining up, right? I'm going to work this out on this side. I know it's already worked out. We're working on this number here, 23.467. And then I'll give my own example. So 23.467. So this may have been written like this, plus 313.21. The numbers may have been written side by side. We don't have the original question. But remember I said when you're adding or subtracting, line up. So when I say line up, I mean make sure your decimals are lined up vertically. So take this off from the right, and then put your decimal on the bottom here, 2, 1, and then 3, 1, 3. Do not add a decimal place here. You're writing the number as is, just lining up your decimals. And then you're adding this. So you want to make a judgment of how many decimal places. Decimal places are the numbers after decimal, right? I got 3 decimal places. I call it DP, my own acronym. 3 decimal places here, 2 decimal places, and then I judge. Of the 2, this is a smaller one. So whatever answer I have to have my answer has to have 2 decimal places, because in the adding or subtracting, the decimal places rule. Okay? So then I add on my calculator. Don't tell my coworkers this. They're like, really? You can't add in your head? I'm like, I can. I just choose not to because I've been doing all this chemistry and I want to give my brain a break. You know, my coworkers, I still like them though. Okay, so I use my calculator. Yes, it's been said and I know it's been recorded. I use my calculator. So I added these 2 numbers, right? And I got 3, 3, 6, dot, line up all the decimal points, then 6, 7, 7. But we said my answer can only have 2 decimal places. So you're counting from the right. This 7 needs to go. Okay, so to get rid of the 7, you round up because it's 5 or above. That number is bigger than 5. So I'm going to erase that 7. Oops, okay. Oh, and then the other 7, because now I have to add that there. So then this becomes an 8, right? And then I have my answer with 2 decimal places. But wait a minute. I thought we were trying to do significant figure rules. Yes, we were. So then I'm going to paraphrase the conclusion. In adding and subtracting, the correct decimal place produces a number with correct significant figures. Okay, it's a means to an end. So what I mean by that is, let's count the significant figures now. We did the decimal place, we did the process right here, but now let's count the significant figures. I have 1, 2, 3, 4, 5. This is 5 significant figure. I'm going to write it to the left because I don't want to confuse it with the rule. 1, 2, 3, 4, 5. This is 5 significant figures. Then my answer 1, 2, 3, 4, 5. When this becomes 8, this is going to be 5 significant figures. Okay, but what I was trying to do was use the decimal place to get the right significant figures. It's a coincidence that my answer has 5 significant figures. I'll give you my own example so y'all can see. Okay, here we're going to be subtracting, right? Once again, decimal place rule, and then eventually significant figures will work itself out. So here the question was 4, 5, 7 plus, plus, not plus, minus, come on, minus 0.68. Okay, so you line them up, right? So you can see right here, 4, 5, 7 minus, there is no decimal here. There's no decimal here. I mean, you can add one if you want, but I'll just say don't even add one. Assume it's there because there wasn't a decimal place in the number. Then you have 0.68. Okay, so here we have 0 decimal places. Here we have 2 decimal places. When you subtract, your answer has to have 0 decimal place. Okay, so 457 minus 0.68, I get 456.32. Okay, this can't be my answer because I have 2 decimal places, but I should have 0. Since both of these numbers are less than 5, I can just drop them off. Don't drop them off and leave a 0 there because 0 still counts as a decimal place. So you want to report your answer as 456, not 56.00 because this is still 2 decimal places, and this one here is 0 decimal place. Okay, so hopefully you understand what I'm trying to communicate. So where was I? Back to significant figure rules. When you're counting significant figures, you count the whole number, not just the part you rounded off. This is still 3 significant figures. This is 2 significant figures, only the 6 and the 8 count. Your answer will be 3 significant figures when you round these 2 off, when they drop off. Okay, so hopefully you can see the significant figure rule doesn't work for the adding and subtracting. It's the decimal place. So you by getting your answer in the correct decimal place, you end up with the correct SF. Here stands for significant figures. It's like a means to an end. Okay, so let me give you guys, I know we have a review set here, and that'll probably take us to the end. Let me give you one weird question on purpose. Oh, let me drag this up here. How do I drag this up? Oh, it won't move. Oh, okay, let me just add the page here. Okay, so I'm gonna write, hold on a second. Okay, so we're gonna add these numbers and try to figure out the correct answer, right? As far as significant figures are concerned, this is 1 significant figure, 4 significant figures, 4 significant figures. Actually, let me add a little bit of yeah, 5 significant figures. I want to add a little bit of drama here. 2 significant figures. But remember, we're not using that rule because we are trying to add. So what do I do with this to add this? Like we have seen, line them up. Make sure that your decimal points are lined up. So I start with my first number, my second number 0.3010, my third number 4.2221, my fourth number. No, I can't count. I start talking, get into all the chemistry, and then I can't do simple things like count, read, figure out left from right. Simple things. Okay, so, ooh, I have to judge my decimal places. I'm trying to get ahead of myself. Judge decimal places. There is none here. Don't just fill it in because you feel that, you know, the number is missing out on something. Don't. 0 decimal place. 1, 2, 3, 4. 4 decimal places. 1, 2, 3, 4. 4 decimal places. 1. 1 decimal place. Right? The decimal place is having a number, any number after the decimal, including 0. But nothing is counts as 0 decimal place. Okay, where was I? Now I add these on my calculator. Yes, 5 plus 0.3010 plus 4.2221 plus 3.1. Okay, so I have 12.6231, right? So can you guys tell me what my answer should be based on what I just did? What is the correct answer when you add these 4 numbers? Any takers? Anybody? Yes. So what should the final answer be? You want to round it up. Because you see how you have a 6 here? Because this number is 5, is big, is equal or greater than 5. So yes. So your answer will have to have 0 decimal place. So it will have to be 13. That's why I gave you all these other numbers here as distractors, right? On purpose. Wait, hold on a second. I'm trying to email a student who has a question. She's supposed to be in this session right now. Okay. Yeah, so yeah, it's going to be 13. Okay. So remember, only these two numbers will remain. So to cancel the rest of this, round it up, and then this becomes 13. Okay. So let's go ahead and practice the other questions that we have here. And then that will pretty much wrap up. Oh no. Let's see. We started at. Have I gone on longer than I was supposed to? I forgot because we started at 9:30, right? Oh my goodness. Okay. What time was I supposed to be done? Okay, you know what? I think I went on longer than I was supposed to because we started at 9:30, right? So we're supposed to end at 11 because the y'all didn't say anything. Y'all need to advocate for yourself. Let me tell you something. I can talk about this for 4 hours, probably. Because I'm looking and I'm saying, wait, are we supposed to be done at 11:30? It's just the class last semester we went to 11:30, so I'm more used to that. But I'm supposed to be done at 11 with you guys, right? So okay, I won't try to overdo this. What I'll do is I'll actually email her and then talk to her about the class because I guess she missed yesterday. We will start this slide here. So I'm gonna write for myself. Start here, okay? Because you know how you guys take more than one class. I teach more than one class. Then I do all this stuff here. So yeah. So when we come on Monday, we'll start here. I'll have a couple more problems just to make sure we're getting the hang of it, and then we'll go from here. Yeah, y'all. If you see me go on and the time is up, just tell me we're supposed to be done until I get used to the schedule. Because yeah. I do apologize. I kept going. And you guys are so good. You just sat there and like, well, we'll just hang in here and persevere through this trial. I mean, yeah, just let me know, hey, we're supposed to be done at 11. But yeah, sorry about that. We'll pick up 9:30 on since I just have you guys. Is the 9:30 a little too early, or are you guys? Because I mean, I don't have any class after you guys on Monday. I just have you guys. Is the 9:30 a little early for you guys, or is it okay? Because I could adjust a little bit if and then we could go to 11:30 if that works. I would rather have you guys at peak performance than to have you guys barely awake. So is 9:30 good? Should we continue with that or should we bump it down to 10? What do you guys say? Because if you have other classes, once again, I'm trying not to get in the way of your other class. Is 9:30 good? Okay. Okay, hey, those who speak up, right? Yeah, it's fine by me too. I just have to get used to it, but yeah, it's fine by me. So yeah, so I won't do this part here. Come Monday, we'll continue, we'll do practice, and then we'll get into the rest of this stuff. I'll try to set it up so it can be a little bit more interactive. It's just kind of hard for me to go from one screen to another, but I'm trying to step up what I do. Yeah. So try to bring in, what is it called, like a multiple choice part where you guys can actually click if you don't want to actually say anything in the chat. But yeah, so we'll start from here on Monday. Wow, I won't see you guys till Monday. When you're working on the homework, if you do have any problems, feel free to email me. It's easier for me with the homework if you take a screenshot and then say I have a problem with this up here, because versus saying number 2A, because I'm like 2A. Sometimes it rearranges from one person to the other, so I have to ask, is this a 2A you're talking about? So if you take a screenshot of what you're looking at, then it's easier for me to actually see it. Are you guys able to view the homework? Because for some reason, even though I did put some dates, it took a couple of tries on my end to see the homework. Were you guys able to see the homework, anybody? At least to do the introductory part? Because I think you guys have, okay, you guys have till Sunday to complete that, right? Yeah, so as long as you can see it, that's fine. If there's anything that you feel you're supposed to see and you're not seeing it, just send me an email. I don't mind. I'm here to help you. So it actually helps me to stay on track, right? If there's something you're supposed to see and you can't see, just send me an email and then I'll fix it. Other than that, if you have any questions. So yeah, for my office hours, for right now, it stays from 2 to 4. I think it's like Tuesday, Thursday, I think. Whatever it says in the syllabus. So but once again, I told you guys, if you have a problem on Monday, Wednesday, don't say, well, she said Tuesday, Thursday, so I can't contact her till then. Just send me an email. As soon as you have a problem, send me an email and then I'll try to address it. I'll tell you when I can address it if it takes a lot more time. Okay. And if not, I'll ask you, are you available right now? Can we meet on eCampus? And then we'll meet and then solve the problem. Okay. Other than that, I'm done. Yeah, I'm done for today. Does anybody have any other questions? Okay. So I'll go ahead and log off. Oh, so before I log off, actually, since you guys are still here, there's something I wanted to show you guys. Somebody was asking about graph paper. You can see all the stuff I do, right? Guys, I really do have a life outside of chemistry. It doesn't look like it. This is just where I do work, so you see a lot of work stuff. But I've had somebody ask me this before. Do I have to use a physical graph? It's really up to you. This app, the Notability, like I mentioned earlier, Notability. As you can see, I opened a brand new page. It does allow you to use different kinds of paper. I like to use the plain white notebook paper. I'm not notebook paper, sorry. The plain white page, but you can have different kinds of page. It's been a while, so I'm trying to remember how to add the different designs. Oh, there, right. You can have, yellow paper like that if you want, if you prefer that. You can have the white paper if you like that. You can have the bigger rules, Once again, they're not giving me royalties for this. This is just to help you, right? If you can't find a graph paper online and you want to use the app, just remember to save as when you're done. You may have to export it. I'm not really sure about that yet, but this is a graph paper. If this is too small, you can use a bigger graph paper. And say I'm using this as a graph paper to do my graph. To draw your axes, once again, you can use, yeah, my hand's a little shaky here. I'm not using a ruler, but when you hold it down, it straightens up. You see? Oops, then you have to let go, then draw. Yeah, once again, my hand is a little shaky. I'm being shaky on purpose, okay. But it straightens up. So you see, I just drew my axes. So you can use that to draw your graph. You don't have to use a physical graph paper if you're comfortable with this. I have people tell me I am more comfortable using a physical graph paper. I want to touch what I'm working on. That's okay. I don't prefer one over the other. I just want you to be comfortable in what you're doing. Okay. Then, of course, you can plot your points right here. That will not change, you know, and then do your best fit line like that. Okay. Any questions about chemistry, the app? I don't know too much about it. I just know just a little bit, just enough for me to work it out. Okay. But I essentially upload my PowerPoint here. If you're wondering, since you guys haven't asked, I'm just trying to fill in the time, even though I'm over. But yeah, I do upload the PowerPoint here. So if you don't want to use a notebook and you want to use the PowerPoint instead, feel free to use, you know, this is a PowerPoint I uploaded this morning. So when the screen was off, I was uploading the PowerPoint, and at any time, you know, you can go ahead, and if you're trying to take your own notes, you can take a screenshot, say this part here, you can capture just part of it, copy, and then move over to your notebook page. So let's say page 2, you want to put that picture here. Oops, I guess I pasted the wrong thing. Some of the stuff I do by trial and error until I figure out what works. Yeah, there. And then you can write your notes. Measuring cylinder. Okay? Once again, up to you. I saw my student use it and I was like, oh my goodness, I thought it was very cool. I was like, I want to be just like him when I grow up. I told my husband, get me that. Then he got it for me. It's helpful because I'm not in an office. I'm at home right now. I don't want to have extra papers lying around. So I just use that to help me. So I still have papers. Okay. Just not too much paper. Anyway, guys, this is all I have for today. So have a great lunch. I guess it's a little early for lunch for some people, but I am thinking about food right now. So yeah, this is all I have. So as far as the way the app looks, let me see. Oh, this is how it looks right here. So you see the little blue, I can't touch, when I touch it, it opens up, but the blue square thing down here, and then that pencil, that's the app. Okay. Okay, guys, this is all I have for today. So we can meet again on Monday at 9:30.